Okay, hello and welcome to this webinar on getting started with TAS systems for NABERS, TM54 and calibrated energy models. My name is Nagman Khan. I'm delighted to host another EDSL webinar, one I've been looking forward to because I've been taking the online e-training on TAS systems. So I'm keen to see how some of the systems pan out here and how easy it is to use things like the systems wizard and some more advanced concepts in a case study coming up later. Let me introduce our speakers first. I'll say hi, Ian, Andrew, and Paul from EDSL. Please introduce yourselves. Hi, Ian.
Hi, thanks, Nagman. Technical Director at EDSL, background in maths and computing, and have been working in the sort of building simulation industry for nearly 40 years now. Thank you.
Thank you. Hi, Andrew.
Hi, yeah. So I've worked with EDSL for about 12 years now. Started as a consultant and then moved to software development. So I've been working on improving the software, and I've got a background in physics.
Excellent. And hello, Paul.
Hi there. My name is Paul Bacon, Director at EDSL. Been working for EDSL for 21 years now. Background is Chartered Engineer in Building Services, and I head up the consultancy department here at EDSL.
Amazing. And let's take a look at the agenda for today. So I'm going to hand over very quickly to Ian, who's going to take us through introduction to TAS and TAS systems. And with Andrew, we're going to talk about getting started using the systems wizard, which is automated interface of using TAS systems. And then we'll look at how to create airside systems in minutes and a look at some more advanced systems, including for part L. And then we'll get on to systems for NABERS and TM54. That takes us nicely on to a very cool case study on One New Change building in London, okay, and how TAS developed a calibrated energy model. As usual, we'll be doing a Q&A at the end. Please post your questions in the Q&A panel or the chat function in Teams here. And if you registered for the webinar, we'll be sharing a recording of this webinar with you in a day or two. Brilliant. Let's crack on. I will hand over to Ian to give a quick overview of TAS. Ian.
Yeah, so the system side of things is obviously simulating the HVAC. So this is sort of airside and waterside systems. What drives this whole thing is the building simulation that we covered previously. And the building simulation will provide heating and cooling demand hour by hour for each of the zones, spaces in the building. And obviously to maintain those set points in the building simulation, you've got like perfect control. So you're just holding 21 degrees, 22 degrees, whatever your set point is. And it's absolute perfection. Whereas when you actually get into the real world, which is hopefully what the system simulation is getting you closer to, you've obviously got control bands, you've got heating coils, cooling coils, all these different sort of airside components, and then obviously you've got the water side as well. And there's a lot more, I wouldn't say fuzziness to it, but you're trying to get back to a much more accurate total energy consumption. And this is the process. You know, airside gives you those demands across to the water side, the plant room, and it's the plant's job then to try and service those heating and cooling loads to maintain set points. And obviously, if the controls in the plant or on the air side aren't quite right, then you're going to see those discrepancies. You're going to see the undershoots and the overshoots. So this is really just refining the modeling to give you a much more accurate prediction of what's going to happen in the real world when you put the real controls into the system. Is that enough, Nagman?
Yeah, let's see how it fits into the wider TAS engineering software.
Yeah,
I think it's.
Yeah, sorry, go Andrew.
Yeah, I was going to say, I think it's worth having an overview of how systems fits in with the rest of the TAS engineering package, especially if you've not really seen TAS before and you're new to TAS. TAS is made up of these 4 or 5 core applications, and they're in red here. Basically, you normally start in the 3D modeler where you define your geometry, but you can also import geometry from external sources. And when you're in the 3D modeler, this is also where you'd go and do daylight calculations. And then when you're done with your geometry, you would export to the building simulator. This is where you would add your internal gains, specify weather, specify constructions, and heating and cooling set points. Also, fresh air requirements can be specified here, and ventilation rates. And then you'd simulate your building simulator file and produce a results file, and that contains your room loads. And this is hourly data for every zone, even every surface in the space. And this is actually the input to TAS systems. So TAS systems needs the hourly load information from the results viewer, the room loads, zone loads. And it also learns information about how the space responds to changes in energy as well, which is used later in the system simulation. And then, so we have a number of supporting applications that go alongside our core applications. We tend to refer to them as utilities. You've probably seen TASGen Opt in a previous webinar. And we've also got things like our TM59 wizard and our UK regulations and 90.1 studios. And the nice thing about the modular nature of TAS is that you can have different people working on different aspects at the same time. And also because these applications communicate with each other via our API, you can swap out bits as well. So for example, if you didn't want to use the 3D modeler, in theory, you could plug in a different front end entirely. So now
sorry, Andrew, that's a really good point about saying that it's important to realize the system simulation. So if you aren't hitting set points and if you aren't meeting those room loads exactly, then you will see the effect, and the building is coupled to the systems. So that's an important point, that the two will interact with one another.
Yes, exactly. So now we can move on to the next slide and look at systems, the layout of the different aspects of the UI in systems, because we're going to be using a few different terms here, so it's good to get familiar with them. So when you create a systems project, each project has an energy center. And this is kind of like the energy accountant, the CO2 accountant for the whole building. It keeps track of the total CO2 emissions and the costs. Oh, someone can't see the slides there. Hopefully everyone else can. But yeah, so this accounts for, it aggregates all of the results across all the plant rooms. And then each energy center can have multiple plant rooms. And the plant rooms are a way of grouping HVAC systems together. So it's kind of a way to organize the data in your project. And then each plant room will have a set of airside systems. So again, that concerns things like fans and pumps, fans and dampers, and
coils.
Coils, yeah, exactly. Coils is the analogous. And the way in which that the airside systems condition the air needs to be accounted for as well, and that's where the collections come in. So say, for example, you've got a fan coil unit and you've got a fan in your fan coil unit. The energy used to turn the fan is accounted for with the electrical collections. If you've got a heat pump, for example, then you would see that reflected in the refrigerant collections and so on. And then also we have things like fuel sources, where you can keep track of tariffs and different CO2 emission rates for each of the different fuel sources in your system. And of course, we have fluids, in case you want to model different properties of fluids that are transferring this energy across your system. Anything to add there, Ian?
I was just about to say fluids. It's sort of like, I've never seen it very often, but sometimes people have got saline mixtures which are slightly different in terms of their physical properties, glycol, that kind of stuff. So yeah, but it's generally speaking, it's just good old-fashioned water with a bit of retardant in it, rust retardant.
Can we do a quick poll? Can you raise your hands maybe if you can't see the slides? Because I've seen a couple of people saying that they can't see the slides. Okay, Mikhail can see. We've got a mix of people who can and can't see the slides. We'll make a recording of the webinar available after the webinar.
Thanks, Tim.
Yeah, thanks, Tim. Yeah, so hopefully you're not missing out too much. And if you stay on, then we can still answer your questions, even if you can't see.
Yeah, it looks like most can see, which is good.
Okay, good. Good to know.
We can blame Microsoft if people can't see. It's nothing to do with us. It's just Teams.
Right, let's get started with systems then. So I'm going to share my screen. There we go. So what I'm going to do is I'm going to open systems, and I'm going to show you very quickly how you can get started with TAS systems. So TAS systems is a component-based modeler. So if, for example, I create a new plant room here, right away you can start dragging in components and linking them together. But of course, this might be quite a time-consuming thing to do if you had to do this for every single system that you're going to model. So this is where the project wizard comes in. So if I press the Project Wizard button here, this contains a number of template systems which we can use to get started, and these are all freely editable. So as mentioned earlier, we're going to create a new project, and then I'm going to select a TSD file. I'm going to use our training course model just for the demonstration purposes, and this will then load in the information from that file, and then we can choose which zones from our TSD file we wish to model in systems. We don't have to model all of them, but we can choose the ones that we want to model. So for this quick demo, I'm going to show the office zones and maybe the extract only zones. And then on the next page, we get to choose what type of system each of these airside configurations is going to use. So if I right click here, you can see the list of all of the template systems. And we also have the 90.1 baseline systems here. And so far, you might notice that this wizard is looking quite similar to the UK Regulation Studio, and that's because the UK Regulation Studio uses the same wizard, just a simplified version that has restricted systems based on what's allowed within the constraints of Part L. So for the office, I'm going to pick fan coil with grouped mechanical ventilation, and then you'll see I can expand this and see all the zones in this group. And on the right-hand side here, these are the properties associated with this system. So, for example, I can change the SFPs if I want to, or decide how the system is sized. And you can see a simplified preview of the schematic that's going to be generated here.
Okay, so sorry, Andrew, just to clarify, what the wizard is doing is actually doing what you were doing earlier. So it's sort of creating the system component by component, but it's doing it automatically for you in the background.
Yeah, exactly. So for the extract only spaces, I'm going to pick extract only, which is quite a simple one, and then press next. And then on this page here, this is where we would decide how we want to heat our spaces. So for this quick demo, I'm going to make a new heating circuit, which is going to be a boiler with a tank, and then I'm going to drag these two across. And so yeah, this creates a boiler with a hot water tank, and the hot water is heated by the boiler, as is the heating for those spaces. And then if I click here, I can also edit the properties of the boiler. So by default, we have one boiler, and I can set the part load efficiencies here if I want to. And I could also add a secondary boiler if I wanted to, and model it in a staged way, whether it's parallel or staged or serial.
I'm presuming you can change the efficiency based on the outside temperature, which is how boilers actually work, rather than flat.
I believe so.
Yeah, okay.
And then I'll do the same for the cooling circuit. I'll just drag this one across, and this will create a simple cooling circuit. And again, you can set the efficiencies here by editing the chiller profile. And domestic hot water. So I created that tank earlier when I set up the heating circuit. So now I can put the domestic hot water demands from these zones and associate them with that circuit. I can also specify the insulation properties of my tank and the size of the tank to model the tank losses. And then if I had PV in my model, which I do actually, then I can associate a surface in the 3D model with a PV panel, and I could also model wind here as well. And I can specify the properties of my PV panel, the efficiencies, etc. here in inverters.
So that PV panel is basically a surface in the building, which has got shading data and everything.
Yeah, exactly. So you can actually specify PV based just on the area and the inclination and orientation, but that won't take into consideration self-shading from the building itself or surrounding buildings. Whereas if you draw it as a surface in the 3D modeler, you get all that shading information across, so you get a much more accurate result.
Yep.
And then on this page, I just need to associate some of my unassigned components with fuel sources. So let's make a new one for the boiler, and I'm going to set that as natural gas. And then I'm going to find the boiler in this list and associate that with the natural gas. And then everything else I'm going to put on grid supplied electricity. So these will be the power for the pumps and things. And then to size our components, we can use a design day. So I can associate all the components with one of the heating or cooling design days that came from the building simulator file. So as Ian was saying earlier, the information from the building simulation file also comes across to TAS systems via the TSD file. So I'm going to create a new design condition and size these components based on the full simulation.
So it's going to run the whole year and figure out what
Yes.
the sizes should be. Okay.
Exactly. And then when we've done this setup, we can just press generate. And it has made our systems for us. So if I zoom in here, you can see that these systems can be freely edited. So for example, this is the heat exchanger that was created. I can double click on that and I can decide if it's only heating only, for example. And if I wanted to, I could drag in more components and connect them up. So it is freely editable. But for now, what I'm going to do is I'm just going to simulate what we've already got. So let's do that. I'm just going to size on the design condition. And then we'll have a look at what the wizards produced.
So anyone who's done a Part L or EPC calculation may not know it, but that's all been generated in the background, possibly without you knowing.
So if I click on this system here and I look at a day where the building's occupied, a day and an hour where the building's occupied, we can see what I've done here is I've coloured the pipes by the temperature, the ducts by the temperature. So the thickness represents the flow rate and the colour represents the temperature. And you can click on the individual components here to see their hourly results. So you can see the condition of the air before it enters and after it leaves the component. And that's the same with the ducts as well. You can click on individual ducts and you can see the individual temperatures. We can do the same for each zone in the model. So we can step through the zones here and see the individual properties for each of the zones. And there's a graphical view here as well. So we can see those results graphically. And when we simulated, if there were any simulation events that we should be aware of, so for example, if we'd undersized our system somehow, then we would see that listed in the simulation events here. We'd see unmet hours here. So if, for example, we were purposefully modeling a specific model of boiler with a known duty, we could enter that information, simulate, and then see for how many hours those set points aren't met. And those set points are the set points that are read from the TBD file. And then I can look at the Waterside. So here we have our boiler that we set up earlier with our tank. And again, this is fully editable. It's so you can create systems really freely here, just like you. So if you've got a real project where you've got quite an unusual Waterside, again, you can model that in detail here and you can just drag in components and connect them up. And if you do make a custom system, then you can actually group these things together and save them in the component library for use on future projects. So that's quite valuable. And then if I click on the results here, this is where we see the overall results for the entire energy center. So we can see the annual demand and consumption. And if we want to, we can break this down into monthly graphs. Here I'm looking at the demand and consumption, but we could also look at, for example, the CO2 emissions. We can run a number of reports in here as well. So for example, if we want to look at frequency reports or sizing reports, we can run those directly from within TAS systems. So I think that's a good general overview. Anything I've missed, Ian?
No, I was about to say show hourly, because that one always spooks me.
Yeah, hourly.
Great overview, Andrew. Andrew, we have a question. How does one change the boiler efficiency based on outdoor temperature? And following on, it says, I understand you can change it based on part load percentage, but not outdoor temp. Is that possible or doable?
You can have both.
So if you double click on the boiler here, for example,
you can look at efficiency, which I think was the question, and then you can add modifier. And you can see there's a part load modifier in there already. And now you can say, there you go, and you can change that to outside temperature and then obviously have the two working together.
There you go, outdoor dry bulb. And you can put in these curves or enter those values as a table. So yes, that can be done.
I'm not gonna buy one of your boilers, Andrew. That was an awful curve.
Yeah, good job I don't make boilers. Right, I'll hand over to Ian then in that case. Or back to Nagman.
should we switch back to the slides? Great. Thank you, Andrew.
And I've got to find Teams again. God. Right.
Yeah.
I'm going to hit share. Hopefully it'll work. Are we good?
Yeah, I can see
Yeah.
that.
So you're going on to the advanced systems section.
Yeah, probably. This was actually a project, I think, in Austria. So hang on, let me see if I can find. Yeah, that was the donor building, which is a bit extreme, I'll be honest with you. That's a bit, I think it's over 1,000. I think it's 1,145 zones. And from Andrew's very nice introduction, you'll see these collections here. So this is the HVAC stuff. So these are the cooling coils in the air handling units. These are the fan coil cooling coils, and likewise on the heating side. This was a bit of a weird one, to be honest. They've got underfloor heating, radiators, and also obviously the HVAC heating coils. I'm just going to quickly run a simulation so you can sort of get a feel for the speed. As I said, this probably wasn't a great one to choose. Let's get rid of that. So that was it, grabbing the TSD information, and now it's just doing the simulation, hour by hour through the year.
Did you say this was 1,000 zones?
Yeah, 1,145, I think.
Wow.
Yeah, so it's pretty rapid. This is one of the slower ones, but the quantity of information it's generating. But it's not surprising, because I think this one is multi-threaded, isn't it, Andrew? Which is probably why we're going relatively quickly. And this PC isn't particularly special. It's just an 8-core, but I think it ramps up to about 5 gigahertz. So quite good. And you'll notice from this system, there's this sort of heat pump sat right in the center, and obviously sorry, can you see my cursor so you can see what I'm pointing at? Yeah, great. So this icon here represents ground loops, and in this particular model we've got 2 sets of ground loops, and then obviously these funny S-shaped things are pumps, and these are heat exchangers, and you're clearly trying to use that ground heat source, heat rejection across this entire loop for the cooling circuit. And obviously if the ground loops can't cope, then you've got a couple of chillers which will cut in and produce hopefully the set point that you're interested in. And it's quite incredible to think that every hour through the year you're taking those building space zone demands and trying to meet it via all of these components and the controls that are going on. So these little things here, oh god, sorry, these are valves, and obviously these are controllers, and if you see this little sort of down arrow, that basically means it's a minimizer, so it's going to try and minimize the signal basically from the inputs it's getting. Likewise that one as well. So you can build some very, very complicated control structures. You can see again here, it's worth pointing out these controllers obviously have a sensor point. So the dashed line is where the sensor is being placed. So the temperature and all the other values that you've got at that point, pressure, etc., are feeding into that controller, and then the controller, you can specify how you want the signal that's being produced to respond in terms of that variable that it's effectively sensing. Yeah, we're getting there. 183.
Ian, while that's running, we have a question from Antonino on the ground loops and how they're modeled. Could you add something to that?
Once this has finished simulating, and I'm beginning to regret doing this now, but I think it's good that you see how quickly it goes. But I can't do anything.
You don't normally have so many zones,
No, it's probably not a great model to be simulating as an example. But no, the ground loops. So I'll double click on one of these ground loops once it's finally got to the end. But as Andrew demonstrated, you can move all of this stuff around. I think one of the most useful things is the wizard and the Part L wizard. They're very good because they give you a starting point. If you were starting with a completely blank sheet and you had nothing, I think you'd probably not struggle, but it wouldn't be quite so easy to produce systems like this. So it's really handy to have those wizards to produce you a sort of starter for 10, and then subsequently you can just augment. And the other sample I'm going to show shortly, which is one new change, that wasn't, I didn't just put that in one go. I started with a relatively simple setup and then slowly expanded the system, because it's very relatively easy to jump in and get things wrong. So there you go, vertical borehole. This is the design pressure drop, so that's what we're expecting the resistance in terms of the flow to be, and that's important in terms of pressures and flow rates, etc., etc. Okay, so this is 100 loops, individual loops, which obviously we pull together. Then you've got the length, diameters, ground thermal conductivity, ground heat capacity. So these are all things that, in terms of one new change, which is the project I'm going to come on to, we were matching an awful lot based on the measured and monitored data that we had. So that was useful. Very useful if you've already got the building built, but it gives you some decent sort of sets of general parameters and a good starting point. Okay, let me just quickly flick to the one new change stuff. Okay, so this is one new change. I used to think this was probably the most complicated Waterside that we've done. I'll talk you through it very, very quickly. At the top here, you've got all of these collections, which are basically the retail heat pump requirements. So these blue lines are basically refrigerant connections. So this is literally, you're talking heat pumps going to indoor units and obviously supplying the heating and the cooling, and you'll see inside, I'm not sure you can see this, but 52, 78 and 2. So these are the number of retail units that are being serviced by these refrigerant circuits, and obviously the heat pump needs to get its heating or heat rejection from somewhere, and this green loop that you can see in the center is the retail primary loop. So this is just a water circuit that just goes round and round, and obviously these heat pumps then pull heat or reject heat into that loop, and that loop, so that's the retail circuit, has to acquire heat or lose heat, and it's got 3 ways to do that. So these are heat exchangers again, this one, and this one, and these are dry air coolers. So it can reject heat via dry air cooling, and it can generate heat via boilers, but it can also connect, it's not a great example because there's not a huge amount of flow here, but it can connect to this ground loop. So there's the ground loop at one new change, and then these 3 heat pumps are representing the 13 heat pumps that they actually had on site, and then this is the office heating loop, and this is the office cooling loop. So all of that flows around, and obviously you get heat rejection or heat acquisition from the ground loop system, and then this heat pump will try and feed the primary retail loop to keep it at the correct temperature in terms of what you're trying to do. And as I say, you've got the dry air coolers which can cool it, and you've also got the boilers which can heat it, but it's sort of in this sequence. So you'll try and do the dry air coolers first, then you'll try and use ground source, and if all of that fails, they'll then use the boilers. It's quite interesting actually, because we were lucky enough to get access to this building and actually go down into the basement and talk to the guys who were running the equipment. When I ran the simulation first time round, these boilers never fired. They just never fired, and I was thinking, oh my God, we must have got something desperately wrong in the modelling. But when I actually got down into the basement and was talking to the guys who actually run the plant down there, I said, the boilers, how often do they fire? And it was like, no, they never fire. And it was like, oh, thank God for that. We've got it. We've actually got it right. So yeah, it's crazy. There's like 1 point something, gigawatts of heating that's just never being used. But again, Paul, you've made this point, which is when the building was first commissioned, and obviously it wasn't up to temperature, they'd have needed those boilers big style. So it's that initial getting the building up to speed, which is good.
Things like COVID as well. When the building's completely empty, they may have needed it to preheat after that. So
Yeah, so I mean it's a sort of fail safe, but when we were modeling this, it was quite fascinating to see that, you know, these things never actually turned on, which is kind of yeah, kind of cute. Yeah, so that's it really. You've obviously got this loop, which again is being controlled. I think it was, I can't remember, it was 5, 10 degrees. It was around there somewhere. And obviously these heat pumps, as I say, are representing the rather large array of heat pumps that they had inside the basement and doing most of the work. I think that's it. I think we've got some more pictures, haven't we, Nagman? In terms of one new change.
Yeah. When
Great.
you're done here, we'll switch to the slides and talk through some of those.
I could probably carry on for a couple of hours, but that's not particularly useful. But yeah, I'll quit sharing now, and we can talk through the remaining slides. Yeah, sorry. Oh, you're back. Great.
It's loading, yeah. I'll just jump to.
We need to buy you a new laptop, Nagman.
There you go.
Yeah. So actually, this is a great one. We were very, very fortunate at One New Change to have all of this information available. It was actually a technology strategy board, TSB project that was funded, I think it was 50-50. And we were working in conjunction with Demand Logic, who have building management system monitoring hardware. I'll explain that in a second, but we're also working with Verco and South Bank University. So it was quite an interesting group, but the idea was to try and figure out not the performance gap exactly, but to just sort of, hey, can we figure out why modeling sometimes isn't quite as accurate as we might think. The interesting thing is if you look at this logged BMS data picture, behind the telephone in the corner, that little box with the sort of silver top, that's the Demand Logic unit that sits on the backnet and snoops all of the signals that are being sent by the BMS system out to the fan coil units, the plant room on the roof, all of that stuff. And it's amazing. They literally log the whole lot to every 10 minutes, 5 minutes. So we were getting hourly averages for everything. And I mean, that was detailed right down to the fan coil unit, 3rd floor, northwest corner, cooling coil control valve signal. So you could literally see every sort of minute detail of what was going on inside the building, and that's what we were using to try and calibrate the model to. BMS screen grabs, very, very useful as well, because that obviously, confirms, the design data that we had originally, is that actually what's going on in real life? And again, the data that you can see here, that's dynamic, you can see what's going on. The tricky bit is if you just tried to work off BMS screen grabs, you're only seeing instance, one instant in time, and what the Demand Logic system was doing was pinging all of that information up into the cloud, massive database, and you could just sift through it and see what you wanted. The weather station, hugely important, because that's actually on the roof of One New Change. So I was actually up on the roof, and I think I took that picture. That's crucial, because that gives you the right solar data, the right temperatures, the right wind speed, the right wind direction to base your building simulation on, which you can then push through to the system simulation. We obviously had utility bills, which is great because that was another corroboration, but trying to create a calibrated model from only the utility bills is a bit of a nightmare, because you can very easily get the right answers for the wrong reasons. So that one's not enough on its own. Again, metered data, which is very handy. And we obviously had the operations and maintenance data, which again was just confirming that the system that we were modeling was appropriate. And yeah, we finally got to within, I think, 5 or 10% of the actual data. So it's certainly, yeah, very, very doable to create a calibrated model. You could probably do without 1 or 2 of these things, and we were lucky because we had all of them. But you certainly need a considerable amount of information to create a calibrated model, or create a decent calibrated model, I think would be a better way of putting it.
If I recall correctly, it was quite nice because you were able to, because we had the weather data and we managed to match up, we were able to predict how much money they would save in terms of energy bills.
That's a very
control. Yeah,
that's a very good point, Andrew. And sorry, I've forgotten about that. Yeah, they were basically looking at massive cooling loads all the way through the year. which was sort of like, hang on a minute, why is it cooling, in the wintertime? That doesn't make any sense. And it turned out to be a humidity control. So the guys at NG Bailey, who were also working on the project, spotted the fact that the RH set point was actually 30%. So the cooling coils was literally working flat out pretty much 24/7, trying to dehumidify, and then they had to reheat the air. So they changed the humidity set point because 30% is very dry, itchy eyes and all that stuff, very uncomfortable. So it made the occupants even happier, which is great. And I think the reason they were particularly interested in what we could do is because they had no idea how much money that was going to save over a full year. Whereas we could run the simulation with the really bad humidity control, we could run it with the better humidity control, and then we could tell them from the energy centre exactly how much cost that was going to save, which turned out to be, I think, £50,000 per annum. So that was the thing they were having trouble quantifying, which the software could obviously model and then reproduce, which is good. Yeah, so this nice picture here is the basement with all the ground source heat pumps. I think there are 13 in total, and this red sort of loop that I've put around these 3 heat pumps, modelled heat pumps, those 3 items actually represent the 13 that are in there. So it's just a quick way of chopping it up so that we can feed, as I say, the office heating and the office cooling requirements, as well as the ground loop. And yeah, those are the actual pipes, the ground loop pipes that go down into the ground and come back up again. So yeah, it's kind of nice to see, not just the basement and the kit that's down there, but up on the roof, the air handling units as well. It's quite nice to get out and see the real world, as it were. Yeah, thanks, Nagman.
Let's take a question on this topic while we're on the slide.
Oh yeah,
Ian.
by all means.
This is open to Ian, Andrew, Paul. How common is modeling to this detail? I mean, this was a few years ago, right, Ian? So presumably you think with all the
10.
Yeah, it was 10 years ago exactly. Presumably with all the increased, you got your BREEAM in use, lead dynamic, NABERS, TM54. Is this happening more and more, or is still not being done to this level?
But geographically, it's quite interesting. In America, they do this. It's commonplace. So if you look at American HVAC engineering, it's right up there. Australia is the same. Not sure about the rest of the world so much.
Germany, perhaps.
Yeah, Germany's probably more onto it than us. In the UK, we tend to be sort of room load centric, and we don't see many consulting engineers doing this kind of depth of analysis in terms of component-based HVAC simulation. It tends to be driven.
It's definitely increased in prevalence in recent years, especially with NABERS UK and TM54. It seems to be a growing area. Yeah. So I think the UK. I'm not saying we're playing catch up, but I don't think we're quite as advanced in terms of HVAC modelling as America and Australia, for example. But no, they've been doing it for decades.
Yeah, I mean to the audience as well, we'd be interested to hear how many of you are doing this level of component level HVAC modeling in your kind of everyday projects. Please, post something in the chat or in the Q&A.
And more importantly, will this seminar encourage you to do it, because it's not that tough?
I think that is a lot of the problems. I think that is a lot of the problems. A lot of people are scared of it, and hopefully this will put their mind at ease a bit.
Yeah, it's really, and as I say, if you've done a Part L or an EPC, this has all been going on in the background for you anyway. And then if you want to take that and refine it and produce a better design for your client, you can then start from those models. You don't have to start from scratch, which I find daunting, I'll be honest with you. But you can start from those models and just tweak them. So yeah, it's good.
There's a good point. We skipped a slide there, Ian. Let's just go back to that quickly if you want to just comment on this one, and then we'll take some Q&A.
Yeah, that's really just pointing out that if you look at that schematic, sorry, cursor again. If you look at this schematic, that's just been generated for you in the background, and you don't know anything about that. You're just doing a Part L EPC calculation. All you really care about is the certificate at the end. But in the process of doing all of this, all of the zones have been, taken account of. All of the systems that you've picked from that drop-down list are being created in the background, and the wizard is basically running all of the building simulations and all of the system simulations to get those final tallies, which gives you your certificate at the end of the day. Yeah.
So with the Part L Studio, if you look in the, because you can't see my cursor, but Nagman, if you hover over in the files in the bottom left there, you can see there's a folder called TPDs. So when you actually do run through the studio, it does produce those systems files in the output folder, and you can actually open them up and run them and inspect them, and you can even use that as a starting point if you really want to.
But you're not allowed to edit them.
You're not. You can't edit them for UK regulations. We're heavily restricted
to get you a better result. Oops.
Yeah, exactly. But they are there, and it's the same wizard that's being used, and that wizard again, it creates all those systems using our automation interface. So quite a lot can be automated as well if you have the resources to go down that route.
It's related to a question there, actually. There's two questions on this. Once the wizard is used to generate the systems and the simulation is run, can you go back to the wizard and add other systems?
Yeah, you can. You can rerun the wizard to add additional plant rooms. But when the wizard runs, it saves all of your wizard inputs as well. So if you want to, you can also run through the wizard again and edit the things that you put in the first time round. So that file is called the TPDX file, and that's produced when you run through the wizard.
Nice. And another question is, would be amazing to connect systems to TM59 so we can have more flexibility around MVHR or tempered cooling. Any comment on that?
Yeah, we've had a couple of requests for that, and it's in the pipeline. That one.
Okay, fantastic. We're going to take some Q&A, so please keep them coming. I'm just going to hand over to Paul quickly to talk a little bit about some of the cool stuff Paul does.
Hi there. As I mentioned, I run the consultancy department here at EDSL. Ultimately, we'd love you all to use the software yourself and do all of the systems modeling, compliance modeling. But if you can't, either because you haven't got the software, you're too busy, or you're just not confident, then we will do it for you. We can take on any project, whether it be a 1-zone model to a 5,000 zone model, and we can do your loads, your overheating, your daylighting, energy calculations, compliance calcs. So even if you have done a compliance calc or carried out many compliance calcs and you're not too happy when it comes to the system side, if you've got to do a TM54 or any other type of energy study, send them over to us and we will take that on for you. And we can sort of show you what we've done as well and sort of give you a bit of training along the way. So if you need any help, then contact us at consultancy@edsl.net and we'll be pleased to help you.
Fantastic. Let's take some Q&A. There's a few piled up. Please keep them coming. We're ahead of time, so we're good in terms of discussion and Q&A. Couple of questions. There was a question early on which I left till the end. That was about SAP, right? More to do with domestic homes. What's the connection between TAS software and SAP? Can you import geometry data? Is it two-way?
There is.
We do have a SAP tool. Yeah, we do have a SAP geometry tool.
I just want to make the point. SAP is a 1 calculation per month. That's 30 plus days. Well, not February, but you know what I mean. It's just they're doing 12 heat balances. We're doing 8,760. So comparing us to SAP is just mental in my view. But I hate the regulatory stuff. So yeah, maybe ignore me on that one.
Andrew, you were saying?
Yeah, we have a SAP geometry export as well. So you can feed that into SAP, and there is some tools there to help you reuse some of your inputs from TAS. But yeah, you're a bit limited, as Ian says, based on the constraints of SAP.
Okay, three technical questions, one on training. How easy is it to model? I'll pose 2 questions together, and whoever wants to answer can do it. How easy is it to model heat pumps in TAS systems? Okay, and second,
I think that's done. We just showed you the heat pumps, and you've got all of those profiles, modifiers. So we've got a whole catalogue of Mitsubishi equipment which is based on their real equipment. So yeah, heat pumps are done. Yeah, that's.
So there was a question though that said, can we model simultaneous heat pumps?
Do you mean in parallel?
I assume that's what the question means, and yes, of course, yeah, we can model that. It just depends how you connect them up in the schematic.
Correct. Yep.
Okay, great. The next question was, quick question: can the software use inch-pound units?
Yeah, yes. I believe so. Yeah, we have.
If you go back to the previous slide, you'll see there's Fahrenheit on the diagram.
Yeah, there you go.
That's for our American friends who still haven't joined the metric world.
That setting is, you can change that in the task manager. There's a settings button at the bottom, and you can change it for all the software just with one drop down.
Actually, sorry, Andrew, which language versions do we have? Because that might be of interest to some.
That is a very good question. I know we have German, and
We had Italian. No, did we have Italian or
We
Russian?
did have
Oh, God.
Italian. Yeah, I can't remember now. We had Russian as well at one point.
Let's carry on with the questions.
Sorry, yeah, it's a bit of a sidetrack.
No, so that was heat pumps. Here's an interesting question. I'm also not sure about this. I've heard kind of rumors or mixed opinions. Can systems help in any way with Part L calculations? Is it even necessary or needed?
It's being used in Part L in the background, so it's already being used in Part L calculations. The problem is the government and the regulations require us to use very specific performance parameters.
Yeah.
Which means, you know, our hands are tied. You know, it's a I can't think of a good analogy, but it's a bit of a straitjacket for us. Whereas once you've done it, and the building might be very different, and actually the regulations are not great in terms of how the dynamic operation of the building might work through the entire year. And that's where systems can come in, take those, you know, regulatory systems. You can augment them and make them much more like the actual design, and then do the simulations and actually know what the building's going to do, rather than what the regulation thinks it's going to do. So yeah, in that respect, I'd say it's incredibly useful. And you know, the regulations themselves are quite useful because they're effectively forcing you to do those calculations. And as I say, with our setup, you get the HVAC schematics built for you. So it's a good starting point.
They can also be used to help calculate seasonal energy efficiency ratios for chillers and heat pumps, because when you get to the compliance calculation, you're very limited to one figure, whereas we can work it out for a whole year and it may give you a much better number, and then you could put that back into the compliance calculation.
Which I believe is allowed.
You can do something with, that's allowed, and I think you can do the same with DSM fans. But there was a funny rule in place that says that we aren't allowed to fully automate that. We did that because other software packages couldn't do that. They wouldn't allow us to put it into the release because we would have the advantage. So we can do it in the background using systems and then feed the numbers back from that back into the compliance calculation and set them as a steady state, sort of, not a steady state, but a fixed SFP. Yeah.
But again, that's allowed.
Yeah.
Yeah, it's allowed. It's just we're not allowed to automate it too much. It's a bit of a strange one.
Two more quick questions. One's about energy storage, specifically ice storage, battery storage, and the second one is about different refrigerants for heat pumps. How to model these?
Hold on a second. Ice storage. Do we do ice storage, Andrew? So I'm going to.
I think we do ice storage, don't we?
I think we do ice storage.
We have ice storage. Yeah, we do that.
We don't have battery storage at the moment, but it's about halfway there because we've been asked for that quite a few times. So that and again because you've got wind turbines, PV, all that sort of stuff flying around. We've actually had a project where battery storage was required, and I did do it, but that required a fair amount of digging around in the code. So it's on the way in terms of battery storage.
In the component library under the coolers section, there's a water source there's an ice storage chiller and a water source ice storage chiller, so they're available and they can be used.
Nice. So what was the other question, Nagman?
Different refrigerants for heat pumps.
Yeah, if you look at the fluid properties, you can change them. So yes, as long as I understand the question correctly, you can change the fluid properties. So yeah, different refrigerants should be covered by that.
Yeah, okay. And if one other thing which is probably worth mentioning, if you do make a custom system, you can save it for use later in the component library. So if you do run through the wizard and then modify a system and then find I need to use that same modified system on lots of different projects, you can save that for later and then use it on a completely different project quite easily.
We probably should try and put this into the video if we're going to post one. You can just literally drag across a group of components a number of components, create a group, and then you can drag that group into the library on the right hand side, and it will turn up as a new item in the library which you can give a name to, and then as that library persists across different models, different projects, and you can just pull it back in again, and then you can ungroup it and start to edit. So yeah, it's quite a flexible system in terms of transferring pre-built schematics via the library into other models and other projects.
Yeah. Let's take a couple more questions and we can wrap up. So one is a bit more specific. So can TAS generate a CIPSI TM52 report? If yes, which methodology does it use? And how easy is it to include the report findings into an NG assessment? So that's very specific around TM52. Second one, a bit more broad and more generic. How would someone get started using TAS systems? Training, resources, documentation. we showed the wizard earlier. What's a great way to get started?
Well, you mentioned Nagman earlier, the online stuff,
Yeah.
and the fact you're getting on really well with it. So I'd say go with the online stuff, but we also do in-person training and online training in person, if you know what I mean. Yeah, so any or all of the above.
I mean,
I'd kick off with the online training.
Training's quite good for systems because you can ask questions, and that can be quite valuable. Like if there's something you don't understand, or if you want to see an example of something in particular, then we can show that live on the in-person training course, which obviously is a bit more difficult with the online training. But also, if you do have a custom system, you're not quite sure how to model it, then if you just email support, then again, once you've been through the training, it's very easy for us to help you on support as well with your custom systems.
Great.
And yeah, to answer the TM52 report question, yeah, we've had TM52 in the software for a very long time now, and it just runs off the dynamic simulation. So you would enter your internal gains properly and run through that, and then you'll get your resultant temperatures out. And then we run through the methodology is actually prescribed in the TM52 document. So we use the methodology which is specified in the document to calculate those results. And yeah, how you want to include those report findings in an energy assessment is up to you. I mean, one thing that we discussed in a previous webinar is that you could actually balance the annual consumptions against the overheating. So you could write an optimization script, for example, to try and make sure that you don't overheat, but also don't try and condition the space to the extent that you're needlessly wasting energy, for example. So those sorts of things can be done.
I think it's interesting the kind of questions we're getting here. It looks like TAS Systems is an incredibly powerful tool, still kind of, tip of the iceberg in terms of what people understand its capabilities, right? So what we'll do is in the follow-up when we share the video, we'll add some extra resources and just answer some more of these questions in a bit more detail.
Yeah,
with some references and links. Yeah.
I saw that Neil asked a question about unregulated loads, and that's relevant for TM54. So when it comes to unregulated loads, we have a load component which you can drop into systems, and you can use that to model unregulated loads. And in that way, that you can account for those loads in your overall graphs that are produced by systems in the energy center. So again, that becomes quite useful for TM54. And then if you wanted to, I mean, for TM54, when you have to model different occupancy scenarios, for example, if you've got uncertainty in your occupancies, then you can go back to a TBD, alter your internal conditions to model, say, for example, different occupancy patterns, and then resimulate through and generate those graphs quite quickly. Because once you change the TBD, all you have to do is simulate your TBD and then resimulate systems, and it will pick up those changes. And then you can export those graphs, those tables and those graphs to Excel to make the various reports that you might want to make, the graphs that you might want to submit for your TM54. For example, if you wanted to do box plots and things like that. The thing with TM54 is it's quite open to interpretation in terms of what you might want to present depending on your specific building. So that's why it's quite handy to be able to export all that information into Excel if you want to do any more sort of advanced presentation work, or even feed it into your own report templates.
Yeah, and you mentioned you mentioned the API earlier. One of the questions here is about feeding in actual performance data into TAS. How easy is that? On the one new change model, was that a custom job? Is that a functionality in the TAS software that anyone can use? So feed in actual data and compare the performance.
Yeah, it depends what you want to feed in, for example. So, for example, we have had people feed in metered data straight into a load component, and then they can attach that load component to the Waterside in order to model the effect of, changing your Waterside on the actual data that went into the load components. That's quite easy to do.
Yeah.
So
basically, you remove the airside modeling and just put a load component in to represent the airside loads, and then you can just do the waterside effectively. So yeah, it's quite flexible. I just wanted to say, I think TM54 and NABERS, I'm not big on the regulations these days, but I think they both sort of nudge you towards doing component-based modeling, which I'm not sure happens a great deal, in all honesty, but it should do, from my understanding of those particular requirements.
So related to that, Andrew, one of the questions Gareth was asking is about matching loads to actual meters and sub-meters, I assume, is the question as well. That is what you're referring to, effectively.
Well, for meters and sub-meters, we're actually in development now. We're looking at a way to add a metering component to make it easier to group certain results together, so it makes it easier to match with metered data. So again, that's something that's currently in progress.
That sounds like the metering hierarchy Gareth is referring to. Another question was, can we have air source heat pumps being able to connect to electrical collections?
Yes.
Now?
Yeah. That's
Okay.
how it works. That's how it works.
We'll elaborate on that, Gareth.
Well, no,
in
it's
a follow-up.
it's you know, there's the air source heat pump, and it's got to get its energy from somewhere, and you assign it to a collection, an electrical collection, and then the electrical collection turns up in the plant room, and then the electrical collection has to be serviced by PV panels or wind turbines or grid supplied electricity. That's it.
Let's take a question on controls, because that's very important and often goes missed and not talked about enough. So the comment is setting up controls, e.g. to sequence all the different heat sources in a complex plant room. It's not very intuitive and is often tricky. Would the controls guide provide guidance that covers most scenarios, or realistically, users will be needing your help from support consultancy in most cases?
We do have quite a comprehensive component guide, which does have quite a lot of controller examples in there, and that's available online. And what we're trying to do is, when people come through with a support question related, what we try to do is we try to turn it into an example and add it to the documentation. So if you do come through with because the nice thing about doing it that way is if you get common questions, then it will very quickly get added to the documentation. So then the likelihood of you needing to contact support should be less. But our support is quite quick. So if you were to use our support service, we tend to get back quite quickly.
Yeah, the other thing I meant to mention is when I was showing that simulation, you probably noticed sometimes it goes quite fast and sometimes a bit slow. And what's fascinating to me is if you've got good control strategies in your model, it tends to run quicker. It's more stable. There's less numerical iterations required because it's a sort of stable system. Whereas if you've got narrow control bands, you've got all sorts of hunting going on, you've got all these sorts of issues, you'll see that in the simulation, and it slows down because it's taking a long time to find that solution because it's fundamentally unstable. So there's more benefit than just being able to predict what's going on. You can almost sense a well controlled system purely on its stability and the fact that it converges very quickly and you get the answers fast.
There's a few more questions. I'll group them together around NABERS, TM54, and more guidance on calibrated energy models. Not necessarily to answer now, but maybe in a follow-up post or email, we can share some guidance on this. I think that there is interest. It's obvious, I think, from the response we're getting here today. There is interest.
So I just saw a question pop up, which is, how many systems can you have? Well, the energy center can have as many plant rooms as you want, and each plant room can have as many airside systems as you want. So it's very much a tree structure. So yeah, that's the way it works.
Yeah, I mean, because we're 64-bit, you could keep going and going and going.
Don't say that, Andrew. People will keep going and going and going.
I think there's a good question here. A good way to round up. We're just top of the hour. Actually, maybe we'll take two. Enrico and I go way back. I always take his question. Similar to the above, is there a way to check at a glance and edit the systems without opening and interrogating the schematics?
Ooh. Not well.
It depends what you want to check, really, doesn't it?
Yeah, I mean, the energy center is the place to start, because if you're suddenly seeing massive amounts of consumption compared to the demand, that's probably a bit odd. So yeah, energy center is a good overview, and then you just drill down basically, because guess what? The energy center feeds off the plant rooms, and the plant rooms feed off their airside systems. So you just have to chase the problem down. But where you spot it is, maybe you'd spot it in the airside schematic, maybe you'd spot it in the waterside schematic, but the energy center is probably a good place to start, just as a sort of sanity check.
You can run airside and waterside reports as well, can't you? And all the numbers are in there, so if anything looks strange in there, that's a good starting point.
Yeah, the reports are good. There's frequency reports as well. So again, if you wanted to look at something that wasn't just unmet hours, for example, if you expected a certain component to behave in a certain way, then you could run the frequency report, and that would give you an idea as to whether it's behaving as you expect. And again, you've got the simulation events window. So anything that systems finds a bit funny when it's simulating, it will make a note of and report in that window. Yeah, and then when you click on one of those warnings, it will zoom you into where that component is and that day and that hour where that event occurs. So you can expect exactly what's going on with that schematic with the values in each of the different places.
There's definitely a lot of potential for a follow-up, either a video or a demo here, Ian, Andrew, and Paul. I think there's a lot of kind of interest here. And like I said, I think it's one of the very powerful tools that most people, even people who are expert TAS users, might not have experience with using TAS systems, right? And it has so much power and capability. Mark had a really interesting question. It's a good way to end, actually. It's referring more to TAS, the roadmap, kind of what's under development, some cool stuff coming out when it comes to TAS systems. I think it's always great for the world to see, EDSL working on really cool technologies coming out. You mentioned already that the metering, you mentioned the energy storage, Ian earlier, battery storage, some more things on systems. Just that'd be a good way to end. Yeah.
Four pipe is something we keep getting asked about as well. So
that's in the software now. That's in 957.
Yeah. Oh, great. There you go.
Yeah, that's already out.
That one's done.
Because the thing is, with the 4-pipe heat pump, again, because it was quite a new thing that everyone was interested in, you could build it already from TAS systems from 5, 6, 7, 10 years ago.
Components.
Yeah, exactly. You just use multiple components and build it yourself. But now we also have a component to make it easier. So that's quite handy. And I mean, the other thing is as well, in terms of future development, we're hoping to integrate systems with Ambience 3D, which is quite exciting. But that'll probably be a future webinar.
Yeah, so that's basically taking the HVAC supplies, extracts, positioning them within the CFD calculation, and then doing that in exactly the same way we do the NAT vent at the moment. Yeah.
Great. Thanks so much, everyone. We're just over the hour. This has been really fun. I feel like there's a lot of interest here, and it's something for EDSL to discuss about what other resources to make available. Ian, I'll hand over to you for some closing remarks.
Yeah, well, thank you everyone for attending. I'm very pleased to see most of you stayed on the call, which is really good for us. And yeah, we'll just carry on doing what we do, which is developing the software and trying to fix your problems. It's as simple as that. It's what we do.
Thanks, guys. Good. We'll call it a day there. Thanks so much for joining. We'll be sharing a follow-up email and the recording and some additional resources to this. Thank you.
Well, I'd just like to say last thing. Thank you very, very much everyone who's giving their positive reactions, because that means a lot to us. Having put the effort in, and yeah, thank you again. Thank you everyone for attending. Yeah, good stuff. Thanks everyone.
Thanks.
Cheers.